Alright, so I'm hanging in my car right now, not quite ready to go in to teach class. And so I thought, hey, why not make a quick video? So let's make a quick video on hybridization. Now, there's already a video that's been posted regarding hybridization, but it doesn't really specifically talk about why things do what they do. So let's take a look at CH4. If I asked you to draw CH4, which we should know is methane, because it only has one carbon and they're all singly bonded. Really, the carbons aren't bonded to any other carbons. It's just one carbon, so it's methane. There's no methane or methine that would exist. And if you drew its Lewis structure, it would look like this. And if I asked you about hybridization, you would have said it's got 1, 2, 3, 4 things around it, so it's therefore Sp3 hybridized. So that's great, but what does that even mean? Well, let's take a look at carbon's valence electrons. So if we were to draw carbon's valence electrons, it has a 2s, and then it has a 2p, and it has a total of 2 in the 2s. Its configuration is 2s2, 2p2, and so it's got 2 in the 2p. And then I said, okay, great, which one of these are bonded in this thing? And the truth is, really none of them and all of them kind of at the same time. So what happens is all these guys get together when they're ready to bond, and kind of like a mixed drink, it's like half and half. You mix them up together and they form a whole new thing, which is kind of in the middle energy level here. So these are ranked in terms of energy. It would be kind of in the middle here, and it would form what's called the Sp3 hybridization. S coming from this S, and then the 3 P's coming from there. So let me draw it a little more clearly so we can make sure we understand. I'll go over here and redo it. So we have, again, a 2s and a 2p, and then in between here, in terms of energy level, we have the Sp3. So this one again had 2, and this one had also 2. And when you mix them together, you're just going to fill out these ones. Essentially, they mix together, and they form this thing. So 1, 2, 3, 4 from the electrons 1, 2, 3, and 4. So we're going to place them in the Sp3. So our Sp3 orbitals, there are 4 of them, and each one is ready for bonding. And this is why carbon would take on 4 bonds with hydrogen. Hydrogen would come in and be like 1, 2, 3, 4, because hydrogen has 1 electron to offer, and there's 4 hydrogens in CH4. All right, let's take another look at something else. Let's go to nitrogen. Try to do this a little better here. So with nitrogen, same situation. It's got 2, again, this is energy increasing. It's got a 2s orbital and a 2p, but the difference is it has 1 extra electron. So it's got 5 valence electrons. So it's got 1, 2, 3, 4, 5. So when they get together and they make the Sp3, now if we go and place these 5 electrons in there, you notice one of them is already paired up. This would make like a lone pair. But these 3 would be available for bonding. And if you make something with NH3, like a neutral compound, where the charge on nitrogen is going to be 0, the formal charge on nitrogen will be 0. If you look at it, this is what you end up getting. And it should make sense because we have 1 lone pair and then 3 Sp3 orbitals available for bonding. All right, let's move on to one more example. Let's look at oxygen. All right, so oxygen, almost exactly the same situation. Energy increasing, has a 2s and a 2p, 1, 2, and it has 6 valence electrons in total. So its electron configuration would look something like that. And then when you mix them together, same thing. you're going to get an Sp3 hybridization. And now we have 6 of these to fill in. So 1, 2, 3, 4, 5, 6. You can look at it immediately and say, hey, look, oxygen's going to have 2 lone pairs on